What is exactly fusion?
Well, that's when two atoms get really close together and form a new atom, releasing energy in the process.
That's what happens in stars.
Yes, exactly. But, Kai, do you think it could be done on Earth?
Anything can be done on Earth. Well, that's why we went to Japan to find out.
Watch the episode to see Kai visit the world's largest tokamak, or fusion reactor, and hear the discussion with one of the world's top experts on fusion and quantum, Professor Peter Fisher from MIT, who will tell us how quantum computers could help achieve fusion on Earth.
Don't go away.
I love looking at the stars. They're so far away and yet I can see them very clearly. A while ago I went to the Atacama Desert in Chile to visit two famous observatories, ALMA and Paranal. Paranal uses optical telescopes to observe the stars and other interesting objects in space using visible light, but ALMA is different. It has an array of 66 radio telescopes to detect what our eyes can't. I wanted to understand how you can see something that is invisible. So I asked our ALMA guide, Danilo.
Please close your eyes. Think in the rainbow. Did you? Now please try to imagine a new color. What happens?
It's hard.
It's hard, isn't it? The reason is because, what we call colors. It is actually how our brain interprets different amounts of energy reaching to our eyes. Human eye was able to detect, to see light in a really, really short range. The shortest wavelengths we're able to observe are something close to 360 nanometers of wavelength. Meanwhile, the longest wavelength we're able to see is something close to 700 nanometers. So, the entire rainbow will fit within that.
Visiting ALMA made me think about stars much more concretely. Why do they shine? After all, it's not just about light or radio waves. Stars produce a huge amount of energy thanks to fusion, when two atoms form a new one and release energy. But how? And can we master fusion on Earth to power our world? Perhaps with the help of quantum computers. To find out if we really can create energy the same way stars do, I traveled to Japan. There are researchers from an international collaboration between Japan and Europe trying to do exactly that, just outside of Tokyo. This is the world's biggest operational fusion reactor, JT60SA. It's called a Tokamak. It's a huge machine as big as a 10-story building, made of super strong steel and giant magnets. It's shaped as a donut with a hollow center where a weird state of matter called plasma lives. Here they are trying to make energy the way our sun does, except in this reactor it's way hotter. The center of the sun is at 15 million degrees Celsius, but on our Earth, for fusion to work, the temperature must be more than 100 million degrees. Wow! To find out more, I asked a fusion expert, Urano-san.
All matter in the universe is made of atoms.
2 down quarks, 1 up quark, and a gluon.
And the matter in the universe consists mainly of hydrogen and helium. This occupies about 99%. But 2 or 3 or 4 atoms combine. So this reaction is called fusion. In the sun, hydrogen nucleus combines. That creates another atom. This is helium. And because of this fusion reaction, so lots of energy is released. So heat and light. That is why the sun is shining. The nuclear fusion reaction does not easily happen because nuclei are all positively charged. This is, for example, the magnet, North Pole attracts South Pole easily. Nuclear fusion is a reaction between the both positively charged particles. So that's why this is not easy. The nuclei never get close enough for fusion, but they just bounce off. How to solve this problem? Then,
You make it very hot.
oh, yes, so we can accelerate the nuclei. This is about thousands of kilometers per second. It's very fast. In the viewpoint of the physics, the speed is equivalent to the temperature and how high temperature we need. This is about 100 million degrees. If you increase the temperature further and further, then the gas state is changed to another state. This is called plasma.
What is plasma?
The plasma is called the fourth state of the matter. The plasma is all around you. The sun is the plasma, and lightning, auroras, and comets, so all those are plasma. So we will make the plasma to create the fusion. We need to accelerate the nuclei to combine the nuclei. Why does the sun make fusion possible? Gravity of the sun is 330,000 times greater than the Earth. So because of this very strong gravity of the sun, nuclei can get close enough for fusion. Gravity of the Earth is very small. We use a magnetic field for fusion on the Earth. For fusion, several Tesla is required.
So by Tesla, do you mean a Tesla, a car, or not a car?
It's the same name. This is the same name, actually. So we use a magnetic field to hold the plasma in donut shape.
Did you know that researchers have been experimenting with fusion since the 1930s? But so far, we've only managed to get more energy out than we put in for a tiny instant. It was first achieved in 2022 at the National Ignition Facility in the US. Now scientists are trying to make that reaction last much, much longer. In 2023, the JT60SA produced 160 cubic meters of plasma, the world's record of plasma volume.
So what actually happens in the reactor when the fusion starts?
High energetic particles are born inside the reactor that create the self-sustaining state. Energetic particle generated by fusion makes the next fusion reaction. And then that next fusion reaction generates another high energetic particle, and that energetic particle causes next fusion reaction. So again and again.
As Uranus-san said, the reactor holds plasma inside with huge magnets so that it never touches the walls. And I really hope that soon this Tokamak, or maybe much bigger one being built in France, ITER will manage to keep the fusion reactor going long enough to produce lots of clean energy for the world.
Kids like me in the future will have very cool technology like quantum computers and fusion.
I hope so. So we'll make a happier life for not only kids but also all people on the earth.
That was awesome! But I really want to know exactly how quantum computers could help us achieve sustained ignition so the fusion reactor stays stable. So I flew back home and invited an MIT University professor, physicist Peter Fisher, to explain how quantum computers in the future could give us a hand with fusion.
Hi, Peter. Really great to have you here with us today on the show.
Good to be here.
We've just come back from Japan. We visited the fusion reactor there just outside of Tokyo.
Mhm.
And Kai still has questions, right, Kai?
Okay.
Yes, could quantum computers help simulate like plasma better than classical computers? And why is it hard?
Well, simulating plasma is hard. You know how a plasma works, right? There are two things you need. Do you know the two things that you need to make a plasma?
solid and liquid, maybe?
Sort of. You need some atoms. Hydrogen's a good atom, and you need a magnet to make a magnetic field. And so you put the atoms in the magnetic field and you pull the atoms apart. So do you know what an atom's made of? Like a hydrogen atom?
I'm remembering back from my quirky quarks game. 2 neutrons, I think 2 up quarks and 2 down quarks.
That's a proton. If you have some hydrogen, you have a proton, that's 2 up quarks and a down quark, and you have an electron, and that electron's its own thing. So that's 2 particles, and you pull them apart, and they get connected to the magnetic field. And what you can do is, if you have a lot of atoms, you can push the magnetic field together and you can make them go into each other. So in Japan, you probably saw a machine that had tritium, which is a proton and 2 neutrons, and deuterium, which is a proton and a neutron. And what you want to do is squeeze those things together. So you pull the atoms apart, you connect them to the magnetic field, and you squeeze them together. And that's the way you get them to fuse, right? Because this is all about fusion. Do you know how many atoms you need?
Billion.
A million, 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 million. And that's why it's hard to simulate a plasma, because you have to keep track of what a million, 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 million particles are doing all at the same time. And then plasmas move very, very, very fast, a foot in about 1/1000th of a second. So you know a billion is 1,000,000,000.
Billion is about 1,000 million.
That's right. Very good.
Well, and then 5 billion, but that's then 5,000 million.
Right. So if you want to simulate a plasma, which means calculate what it's doing for a second, you have to do 1 billion calculations of what a million, 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 million particles are doing. That's why it's hard. That's the biggest computers on Earth couldn't do that right now. And so we hope a quantum computer can. There's not a quantum computer right now that's better than a classical computer. It's very close, though. You're doing this at a very exciting time.
What about current research? Are we doing anything with quantum and fusion today?
Actually, we are. We have a big laboratory at MIT called the Plasma Fusion Science Center, and they are doing a lot of work at Princeton, doing some quantum simulations and then comparing them with classical simulations to make sure they understand what happened. When I was at school at Caltech, one of my teachers was Richard Feynman, who was kind of the founder of quantum computing. And he told us nature is quantum. So if you want to simulate nature, you better use a quantum system. So if a plasma is a quantum system, and so they're trying to mirror a quantum system to do calculations.
How was it knowing Feynman in person?
Different. He's different than any other human being I've ever met. He was a great scientist and a great calculator because he already knew what the answer was. I don't know how he knew, but it's a lot easier to get the right answer when you already know what the answer is. And I talked to him a lot. He could be a very difficult person, but he was always interesting.
So actually, could quantum computing help or improve how we design tokamaks?
I think this quantum simulator already is. So we are very excited here at MIT because 5, maybe 7 years ago, a professor was teaching a course about tokamaks. The guy's name is Dennis White, Whyte, and he gave the students an assignment, a little design assignment. And one of the student groups solved the problem in a different way that involved making the tokamak much smaller and much higher magnetic field. And they got a very efficient result. And so Dennis thought they were wrong and was about to give them an F. And he worked it out for himself and discovered that they had actually stumbled on a different way of designing a tokamak. And one thing led to another. And there's now a company called Commonwealth Fusion that's near MIT, and they are building a reactor, and they are absolutely convinced that they're going to reach scientific break-even. Do you know what that is, Kai? Scientific break-even?
Maybe.
What does a fusion reactor make?
Energy, and that energy
And that's what
is
you
then
sell.
used.
That's how all of this works, is that they make energy. So scientific break-even for fusion means that you get more energy out than you put in. And only one fusion reactor in history has done that, and that's not a Tokamak. It was done a few years ago at the National Ignition Facility in Livermore. And this was a very big deal. And I want you to remember Commonwealth Fusion. And the name of the machine is Spark, SPARC. And it came from a
Spark.
student's assignment. So this is why you should always do your homework, is you never know when you're going to write something down that's really important.
Yeah, exactly. That was in 2022, right? They achieved this result, I believe.
The NIF, yeah.
Yeah, yeah. That was a great one.
Oh, I was so excited by that. I know a bunch of people who worked on the project, and one of them, Amy Kriker, the whole thing was to design a fuel pellet, which is about the size of a head of a pin. And it was very complicated. It had to be frozen. It had to have a little kind of pipe in it. And she worked on this for a decade. It worked.
Oh,
I just want to quickly say that that thing about decades, it's like when I am sewing and I take a needle and try to put it through the hole. That's what it feels like. Decades it takes to just
so it takes a lot.
That's great, Kai. Think about if the needle was 10 atoms across and the thread was one atom, a row of atoms. That's how small it is. You just have to line it all up.
I'll just use a microscope to see it like this.
You just have to line it up and get it right.
So how would you say quantum computers could help us understand the particles inside the plasma?
Well, so the quantum computers will actually, as a simulator, undergo the same motion as the particles in the plasma, but it will do it in a controlled way where you can measure everything. It's very hard to measure things in a plasma because it's very, very hot. So you can't just stick a thermometer in there because it will melt. A lot of light comes out. So you have to measure the intensity of the light, but the light comes from different places inside the plasma. So it's really, really hard. So if you have a simulator where you can control everything and it's maybe 1,000th of the size and they're smaller, it's just a small part, but you can set everything up the way you want and then see how it moves in a much more direct way. And that's a version of a quantum computer. Do
Okay.
you use a computer at home yet?
Yes, I do. It is, by the way, resting in its charging spot back there.
Okay. But it's not a quantum computer.
That would not fit in my room, I can tell you that.
Probably not. Probably not. They're quite big these days, but they'll get
Yeah.
smaller.
Yeah, and my computer could easily just be this big and fit. Then having a big quantum computer that would not fit.
Well, but the quantum computer will be able to do things no other computer can do.
Can you get a new house that is bigger to fit?
With a quantum computer,
Well,
absolutely.
you don't want to live with the quantum computer. What you really want is someone else to buy the quantum computer and let you use it.
Mm.
That's a good way to approach life in general, which is not have your own things, but get to use other people's things. That's the nice thing about universities. You just
That's
get to go and use the university things.
And what about is the magnets in the Tokamak? Could they help design better magnets to hold plasma in place?
Well, yes. So one of the most important things about the Spark project that I told you about are the magnets. So the most powerful magnets in the world were at CERN, and the team that's building this Spark machine made magnets that are about 5 times more powerful, and they're small. And those magnets can be used for a lot of other things. Do you know what a maglev train is?
No.
Mag means magnet, lev means levitate, is if you have some really powerful magnets the train
Well-
floats on the magnets.
Here, I've seen this on like special trains that you'd have a magnet and then another magnet, and then if you'd have the north pointing down and south pointing down to both north, then obviously the magnet will go inside. But if you have a lot of these, giving the magnet no choice to move on side, it will just go up and then levitate there.
Exactly. So trains like that are possible because of these new magnets that were made for this fusion machine. And there are lots of other important places magnets get used. So Commonwealth Fusion's very, very excited, not just because they'll probably make the first or the second fusion reaction to reach break even, but because they can use these magnets for a lot of different exciting things like very fast trains and things that can take pictures of your brain while you're thinking.
So you mean taking pictures inside of the brain?
It's called MRI.
Yeah, exactly.
Well, does it hurt?
It doesn't hurt, but if you're unlucky and hurt yourself, they use an MRI to see where you've hurt yourself. If
Yeah.
you're lucky and have a friend like Rebecca Sachs, who's a colleague of mine here at MIT, she has her own MRI machine. So you can go use it.
In your opinion, if quantum computers do indeed help us achieve fusion energy on Earth, what would be the first breakthrough that we might see?
You know, in the realm of scientific discovery, I think that would be such a monumental achievement. Just that it would be like landing on the moon. It would, I mean, I'm not joking because people have been trying to do this for 70 years. And so it would be a launching pad for things that I'm not even sure we could imagine. I think the first most exciting thing is that you'd really know what you need to do to ensure an energy supply for the human race, because fusion is probably the only thing that's enduring, because everything else relies on elements that you have to get from somewhere. Whereas fusion, it's hard, but you don't need any really weird chemicals or compounds or things. So I think it would change the way the world looks at itself. It's a very, very exciting time.
Fantastic. Thank you so much, Peter, for joining
Thank
us.
you. And I'm happy to come back and tell you about dark matter sometime.
Oh, that would
That's
be
what I-
fantastic. Well, we'd also like to thank, of course, Fusion for Energy and NACA Institute for Fusion Science and Technology for helping us produce this episode. That's why we even managed to go and visit the Tokamak in Japan.
And thank you to our viewers. Don't forget to click that like button and the subscribe button.
That's
Or
it.
like and subscribe.
We hope to see you next month for the next episode of The Quantum Kit. Thank you so much again, Peter, for joining us, and goodbye.
Bye!